So hello, my name is Brian Evanko. I'm a second-year graduate student in the materials department here. And today I'm going to give a brief introduction to supercapacitors and talk about how we are enhancing their energy density with redox-active electrolytes. This is a really interesting project because it's managed between three universities. We have P.I. Shannon Betcher at the University of Oregon, David G. at Oregon State University, and Galen Stuckey and Dave Austin here at Santa Barbara. And these are all under one umbrella of the RPE grant that was just mentioned. And we're about 1 year into a 3-year project at this point. So a good place to begin with supercapacitors is our Argonne plot, which shows many of our current energy storage technologies and their range of energy stored and specific power. So usually we only think about the specific energy axis, which is how much energy an energy storage device can hold per unit volume or per unit weight. You can see, I'll use this pointer here. Yeah. You can see a car battery here, lead acid, relatively low in terms of specific energy. A little bit higher is nickel metal hydride, and then lithium ion batteries. The reason we use lead acid is because they're cheap, even though they don't have the energy density of lithium ion. But what we don't think about as often is the specific power. And one example I think is really useful to illustrate the importance of specific power is regenerative braking in automobiles, which is an emerging field. When you are moving at high speed in your car on the highway, many of you are probably already familiar with this, you have a large amount of kinetic energy which you waste as heat when you apply your brake pads to the calipers in your wheels. If you have a hybrid or a fully electric automobile, you can, instead of wasting this energy as heat, drive your electric motor in reverse, because an electric motor driven in reverse is a generator, and this can actually store electrical energy back up for your next acceleration period. The problem is that this is a large amount of energy over a very short interval of time, which is a high power, and lithium-ion batteries cannot absorb such high power. You'll damage the lithium-ion battery pack. So you need something to go in tandem with this. And a good candidate is electrochemical capacitors, because although they hold much less energy per unit weight, they can absorb energy and deliver it very, very quickly, up to an order of magnitude more quickly. Additionally, these supercapacitors, which you'll also see called ultracapacitors and EDLCs, can cycle tens of thousands to millions of times. So their life cycles are very long because they don't have expansion and contraction of the electrodes that you get in a battery. So they're very stable. They also will likely have an increasingly important role in the grid energy storage. As renewables increase fluctuations in the grid, this will help deal with those fluctuations. We're trying to target a device that operates in this regime about 15 watt-hours per kilogram, only about 10% the energy density of a lithium-ion battery, but at a higher power density than even high-powered lithium-ion batteries. So we're really just trying to push over the energy density of electrochemical capacitors. Before I discuss how we're going to do that, this is a brief review of how energy is stored in a capacitor. Traditional capacitor is just two conducting plates separated by insulating dielectric material. And as you apply a potential across the plates, you move electric charge from one to the other, and energy is stored in the electric field, this potential electric field between the plates. Capacitance is a measure of how much charge you can separate for a given voltage. And it's proportional to the permittivity of the dielectric times the area of your conductive plates divided by the distance between the plates. We can engineer materials to have high permittivities, but to increase the area and decrease the distance between plates, we have to manufacture extremely thin structures, which is difficult to do without defects. And there's a trick with supercapacitors to get around these obstacles naturally. Supercapacitors are very simple. It's just two activated carbon electrodes. Activated carbon is cheap material similar to what you find in a Brita water filter, submerged in an electrolyte. It can be an organic or aqueous electrolyte with dissolved salts. As you build a positive charge on one activated carbon surface and negative charge on the other activated carbon surface, you separate the cations and anions in the electrolyte. And you're storing energy in the electric field between this layer of dissolved ions and this layer of surface charge. And it acts as two capacitors in series. The area term is immense because activated carbon has specific surface areas on the order of 1,500 to 3,000 square meters per gram. And the permittivity is high because we're typically in something like water, which has an excellent permittivity. Finally, this distance of separation is on the order of angstroms because the only thing limiting us is the solvation shell of water around the ions. So we naturally approach the limits of most of these variables. The drawback to supercapacitors is we cannot go to high voltage. Energy stored in a supercapacitor is equal to 1/2 of capacitance times voltage squared. And because these are in electrolytes, if you push voltage too high, you break down your electrolyte. This is a typical charge-discharge curve for a supercapacitor. And as you charge the device and separate more and more charge between the electrodes, the voltage of the device increases. And once you reach the limit of the electrolyte, you have to stop charging. Then you discharge and get your energy back. The energy stored is proportional to the area underneath this curve. And right now, 5 watt-hours per kilogram is about the limit of commercial supercapacitors. The fundamental idea behind this project is to add 2 redox couples into the electrolyte. One redox couple can be driven at the anode, and the other can be driven at the cathode. And when you charge this device, it looks exactly the same for the initial parts of the charge. However, once you reach a sufficient voltage to drive both redox couples, you start to see a more battery-type behavior, where you have these plateaus. You can see the area under this curve increases dramatically. And we get much higher specific energy densities, maybe 20 watt-hours per kilogram. And this is just the first generation where we oxidize iodide to triiodide upon charging and reduce vanadium 4+ to vanadium 3+. And what you would expect, intuitively, you would think that as you reduce this and oxidize this, your ions are going to diffuse across the device and discharge. And we've engineered ways to overcome that by choosing couples that remain strongly adsorbed to the activated carbon after they undergo reduction or oxidation. So the device actually can be left to open circuit potential for a long time without internally self-discharging, which is good for a capacitor. You see, though, the charging voltage in the battery regime is only about 0.4 volts. It's relatively low. So at the University of Oregon, they've begun with looking at new chemistry. This is methyl halogen bromide system. And they can push that plateau all the way up to about 1.3 volts, which extends the energy density significantly. And what we're looking at here is the individual potential of the positive electrode. You can see it has a capacitive region and then a battery type charging region. And the negative electrode has the same capacitive region followed by a redox battery type region. And then the sum of the voltages of the 2 electrodes is your overall cell potential. And this slide shows us that we can, in fact, have relatively low self-discharge rates. And when we charge to 1.4 volts, which is the full voltage of the cell, we can get specific capacities approaching 40 watt-hours per kilogram. And this 40 watt-hours per kilogram, after sitting open circuit for 6 hours, still retains about 60% of its energy, which would be terrible for a battery, but it's excellent for a capacitor, because most capacitors are discharged relatively quickly after they are charged. And this was not expected that these redox couples could be, it was not expected that we could sufficiently solve this self-discharge problem, and that's been a big success in the first year. And you can see the this black trace here is an inert electrolyte, no redox active electrolyte in the cell. And that is about 5 watt-hours per kilogram. And it's just amazing the amount of energy density increase we get by adding redox couples. So far, all of this work has been done on the benchtop scale in swage lock cells and specially designed electrolyte volume limiting cells. But a lot of battery and supercapacitor research does not scale well that you see in literature. And our next aim is to prove that we can make a large-scale device, engineering it here at UCSB. And we'd like to make a device in an 18650 format. This is a good choice because it's an industry standard, and it has a similar volume to a very popular commercial supercapacitor, so we can make pretty direct comparisons between our electrolyte and commercially available technology. We're aiming to increase the specific energy density by about 3 times. We will have slightly lower specific power, but still much higher than a battery. So again, we're trying to take the advantageous high power density of a supercapacitor and high energy density of a battery and meet somewhere in the middle to fill these grid storage and electric vehicle applications. And we also would like to have a wide operating temperature range so that we could maybe replace lead-acid batteries in cars and have cold start capability. And that could be very interesting because of our constant voltage that is delivered during the discharge will be advantageous for a lot of those engineering applications. Whereas currently, using a supercapacitor bank as a drop-in replacement for lead-acid battery is not feasible because the voltage drops off as you try to use it, and so you need conversion power electronics, and this stable discharge plateau may help us work around that. So we've recently finished assembling this 18650 prototyping line, which some of you saw this morning on the tour. We have a Dr. Blade coater to make large electrode films, and here's a sample right now. This is maybe not that impressive, but it's very large compared to what you would typically make in academic research. And we now have a roll press to make these have very high uniformity and quality. We also have a beating machine and a sealing machine to seal our chemistry and electrodes into these 18650 canisters, which again are about the same size as popular commercial supercapacitor devices. And we have also added the capability to test under very high current densities with this high power cycler and under a variety of temperatures with this environmental chamber. So we can simulate how these things will perform in real world conditions. And together, these things have really added to this recent remodel of the Materials Research Laboratory Battery Lab. And we're excited to scale up these chemistries that they're developing in Oregon. Now I'd be happy to take any questions that you might have. Thank you.